let's take a look at a really neat example of using antiderivatives that maybe some of you have seen before. The equation for the motion of a falling object. We've got a really nice formula for this, for an object in free fall, and usually it's just given to students either in an Algebra 2 class or in a physics class, and you're just supposed to trust it. But one of the joys and the powers of calculus, especially once you're able to take derivatives and antiderivatives, is you can derive formulas for how the world works from some really key basic principles. And falling objects is a great example of that. So recall that position, we're going to use S of t. And position in this case is just how high is an object. We're not going to worry about left to right motion right now. Velocity, that v of t, that's just how fast this is changing. The position is changing. And acceleration, a of t, is just going to be how fast velocity is changing. Both of those can be negative. So to tie that more into our calculus, remember that v of t is equal to the derivative with respect to t of position, and acceleration is the derivative of velocity with respect to position, which means that is the second derivative of position. Okay, so you ready? To get the equation for the height of a falling object somewhere near the surface of the Earth, all you need to know or believe is that the force of gravity has a constant acceleration. That is the only thing acting on our object is just gravity, and that acts with a constant acceleration. In metric units, that is negative 9.8 about. So if you're keeping track, meters per second squared. It's negative 32 if you're in feet per second squared. We'll stick with metric for this example. And that's it. All we need to know is that there is a constant force, a constant acceleration, negative 9.8. And from there, we can come up with an equation for its height, for its position, S of t. Let's do it. I have a of t. Let's find its antiderivative. Well, its antiderivative is v of t. That negative 9.8 can hang out. Times 1, the antiderivative of 1 is just, well, not an x, but a t. And we should be able to check if I take its derivative, yeah, I get negative 9.8. But we also need this plus a constant. We don't know what that constant is yet, and that is okay, but it's something. Next, we could say, what is position? Well, position is the antiderivative of velocity. And so that negative 9.8 is going to hang out. What is the antiderivative of t? Well, it's going to be a t squared, and then I need to divide by 2 to make sure that when that 2 comes down, it cancels out. Plus, don't forget this c. This c now has an antiderivative, c times t, and the whole thing gets another constant. Okay, so that if I took the derivative of s now, I would get v of t. So you can always check by just taking the derivative and seeing that you get what you're supposed to. Okay, let's clean this up ever so slightly. This is negative 4.9, right? 9.8 times 1/2. T squared plus c t plus d. That's starting to look a lot better. That might even look familiar, but we can do better because c and d don't have a whole lot of meaning. What we need is some initial conditions, and I'm going to do this really abstractly to make it look as best I can, probably like what you've seen, if you've seen this before. We're going to say that my position has some initial value. It's going to start at some initial height. We're just going to call that h naught. Whatever that height is, it's just the constant h naught. But also my velocity has some initial value, and we're going to call that v naught. Now let's use these to see if we can get rid of those c's and t's. Sorry, c's and d's. So first off, let's go ahead and plug in here. At v of 0, this should be v naught. And if we plug into that velocity function, what do we get? We get v naught is equal to c. Similarly, we could plug in to our position function at time equals 0. That should give us an h naught, but we could plug in and get negative 9.80 squared. Sorry, negative 4.90 squared plus c times 0 plus d. But that is just h naught equals d. What do we get if we put this all together? We get our old friend. Maybe a new friend if you're just discovering it. negative 4.9 t squared plus whatever speed you start with, whatever velocity you start with, times t, plus whatever height you start with. And hopefully this makes a little bit of sense, at least that plus h naught, because all that's really going to do is add some height to wherever you're at. Whereas my velocity, I need the velocity times time to see how that's going to affect my position. This is the fun, amazing formula for the height of a falling object in free fall somewhere near the planet Earth. Okay, doing this out in space is actually not that much different. If you're on, like, say, the moon or Jupiter, all you're going to really change is that 9.8 to whatever the appropriate number is for that planet or moon. I think that's pretty neat, seeing that we can derive physics just by knowing a little bit of calculus.